Okay, I'm going to get started. So today I want to tell you about in a way a model for computation that we've indirectly referred to several times in this course and also I think on the homework. It's called the query model, the Oracle model, the query complexity model. And in fact, all the quantum algorithms that we've looked at so far essentially work in this black box query model. In fact, perhaps arguably all the quantum algorithms that are cool that we know work in this black box query model. So I want to talk about formalizing it today and some results in this model. So what's going on in this model? So you're given as the input some data, which we've normally been writing like this. There's a function f mapping some set of size capital N into some other finite set, which we've been calling colors. And today you should really think of it as like a table or a list or an array of data items, numbered 0, 1, 2, 3, 4, et cetera, and I don't know, red, green, blue, et cetera. So some of this is the input, but you're not given it really explicitly as you are in like normal computational model. Rather, you're given it by this like quantum circuit. This is what we've seen so far, QF, that computes or implements f. Okay, so you're imagining you have like some sort of box. Well, in fact, you've always had this like box QF that we didn't really pry into. We just assumed that it gave us access to some data. Okay, and the task was to solve some problem about this data, capital F. And later in the lecture, I'm going to start calling these problems phi, just because I needed some letter. So the problem will be called phi. Okay, and all the algorithms that we've seen so far quantumly fit into this framework. I listed a few of them here, but the other ones like Shor's algorithm, in some sense for order finding, Bernstein-Vazirani, they all work like this. So just to remind you one more time, Simon's problem was you're given this data f, and it had this periodicity property that f of x is equal to f of x plus s. This is addition in mod 2 in this domain. For some non-zero string s, and all the other pairs are promised to be distinct, and your task is to find s. The hidden subgroup problem was some generalization of this to a group setting where f was periodic with respect to shifts by elements of a subgroup, and you had to find the subgroup. And last class we talked about Grover's problem, which is actually in some sense the case where this colors is just 0 or 1, so you have like a long list of bits. And the task is to find some position x where f of x equals 1. Or else, certify that there is no such x. And really, this problem phi is just like the problem of computing the OR of the data, the logical OR of the data. So what I want to emphasize here is that in all our quantum algorithms for solving these various problems, we kind of just assumed that QF was like a black box that was given to us, and we never really pried into how it worked. I mean, we didn't care about what gates QF was composed of. The only thing we really did to it was apply it, or query it, as it's called. We applied this circuit, if you will, to inputs, or sometimes superposition of inputs, and got back our answers, and that was it. So it was kind of, we used this QF in a black box fashion. And that's going to motivate the formalization of this query complexity model. And just also mention, in almost all cases, the overall complexity, if you actually did count up all the gates of the quantum algorithm, was essentially dominated by the number of times you applied this QF. Okay, so I mean, that was the main factor in the overall complexity. The one exception was this thing I alluded to, but didn't get into too much details. For this problem over non-abelian groups, it was known how to solve the problem efficiently in terms of how many times you applied this black box QF, but it wasn't known how to solve it efficiently in terms of overall gates. But in most of the popular cases, like Shor's algorithm, Simon's algorithm, and so forth, these were roughly interchangeable. Yep?
So just like we can think of all these function problems as decision problems, can't we think of everything as a query problem in some sense?
Well, I want to make it in distinction, so I'm going to define this query complexity model now. But it's in distinction to let's say if you're using Grover's problem or Grover's algorithm to solve SAT, where you're given a classical circuit C, and you want to find a satisfying assignment for it, an input that makes it output 1. You can do that by first turning it into a quantum circuit, and then doing this sort of black box or computing algorithm, just using the quantum circuit as a black box. And in principle, you could instead like kind of try to analyze C. You could simply with a quantum algorithm like look at the gates of C and try to figure out what this circuit is doing in order to help you find an input that makes it output 1. But we're going to be focusing on this other approach where you sort of just use C as like a black box, or its quantum analog as a black box. Only its input-output behavior. OK, so this motivates studying a different sort of model for algorithms called the query complexity model. And it's a model that you can use actually to study the power of randomness, to study the power of quantum, which is what we'll be focused on, and study the power of other kinds of computation. But OK, so in the query complexity model, you don't have like a normal input exactly as you do in normal computation. Rather, like you have this, let's say, Q of f, and it's considered like a black box. Or sometimes it's called an oracle, which basically means you're only allowed to apply it. You're not allowed to look into how QF is composed of gates. You should, in fact, just think of it as like some magic box that somebody gives you that gives you access to some table of data at capital F. OK, so that's one aspect of it, this quantum complexity model. I'll redraw this in a second. But the main difference is the kind of the cost model or the complexity model, or what we count as efficient versus not efficient. So continue this. In this model, the cost of an algorithm to solve a problem, some problem phi, is just defined to be just the number of times you apply QF. So in some sense, you only charge yourself, 1 every time you look at, an item in the input list. Okay? And in particular, like all other computation you do is quote unquote free. So what that means is, if you're the algorithm, you can like think for an extremely long time, very carefully run any algorithm you want to decide like which item in the input list here you want to look at next. Finally, you decide, you might use randomness, and in the quantum model you might decide on a superposition of inputs to ask about. You think for a long time, you make your query, you find out about the inputs, and that costs you 1. Then you get back the answer, and you can think for a really long time about what to do, and then decide to make another query, and so forth. And we're just going to say that the cost of the algorithm is the number of times you apply this black box. So I'll talk about like if it's reasonable to study this model, and as opposed to like the normal model where like the input is sort of explicitly given to you, and you measure the running time of the algorithm, the number of steps it takes, or in the circuit model like the number of gates you use. But let me just emphasize that in this model, you can study several variants, including the deterministic variant, classical randomized, and quantum. In fact, you can also study additional models like non-deterministic model, other models, but we won't talk about that much today. OK, and this model just means that like the algorithm has to be deterministic, so it always, in fact, queries the same entries in the input data. Here, you're allowed to use randomness to decide what to query next, and here you're allowed to, well, you can use randomness, but you can also mainly query superpositions of F's entries. OK, so this is kind of like a new model for computation, or at least like a new way of measuring the cost or efficiency of an algorithm, only charging for like essentially how many times you query the input data. So one might ask, why study this model? I'll give you some answers. Okay, so answer number 1 is, as I said, well, all our quantum algorithms do sort of fit into this model. Okay, so in light of that, it seems worth codifying the model and trying to study it in its own sake, since the algorithms we've been studying all sort of fit into it. 2, I mentioned this in words before, but usually, let's say, the ignored computational cost is pretty cheap. So it's, like maybe little n to the constant, which is log of capital N to a constant. Gates, or time per query. Okay, so for example, when we were solving Simon's problem, the main step was like doing one query to QF, and that gave us essentially one clue about the unknown string S. And so we did it little n times overall. And every time we did it, we also had to do like a Hadamard transform, which was like little n gates. But, roughly speaking, the cost is proportional to the number of queries. Okay, and the third reason we should like to study it, and it's a very nice reason, is it's a simple model. And in fact, so simple that it's feasible to prove lower bounds. Which means, impossibility results, or, no-go results, as they call them sometimes. So if you know a little bit about, computational complexity theory, like you know that we're extremely terrible at proving any kind of negative results about the power of algorithms. We cannot even prove that p does not equal np, that there's no polynomial time algorithm for the SAT problem, even though it really seems true. So that's a shame. But this model, it's a different model that just counts, the cost of querying the input. It's simple enough that it's quite easy to prove negative results. And that's nice. I mean, it lets you decide often whether the algorithms that you've come up with are optimal, at least within this framework of quantum query complexity, which all your algorithms happen to be fitting into anyway. So for example, in the next class, we'll prove something that I mentioned last time, which is that for Grover's problem, which is the problem of computing the OR of capital N bits, you can prove that even in the quantum model, roughly root n queries are necessary. Okay, that matches the upper bound that Grover proved, that on the order of root capital N queries suffice. Okay, that's very satisfactory. I mean, it goes to show that, at least within this query complexity model, Grover's algorithm is optimal. And finally, this could somehow give evidence about the power of different models, like randomization versus determinism versus quantum versus non-determinism and so forth. Okay, so I can give some kind of evidence at the level of computational complexity theory, which we won't really get into. And it's debatable how strong evidence it is, but, well, it's something. Yeah?
Is there any setting where, the lower bound you obtain in this, I guess, artificial construction somehow generalizes to, the Turing machine models? Is there any case where we come up with a proof where the lower bound for the system is what else is it going to do other than try all of these 2 to the n possible combinations, and then you take that proof, tweak it a little bit, and then it actually works in general cases? So even if the exponential lower bound turns into a linear lower bound or something like that?
Basically, no.
Okay.
Yeah, we basically can't prove anything in the usual model, except by diagonalization, like these time hierarchy theorems. That's pretty much all we got. It's life. OK, so any more questions about the model? Now we're going to try to start studying problems within this model. OK, so I'm now going to change all the notation, which is annoying. But I feel like I want to do it because ultimately it's a little weird that your input, for example, I drew it here and erased it, just looked like a list of like red, green, blue, red. It's sort of a little bit weird to think of that as like a function on x. I mean, it's just like a string, right? That's how we normally think about inputs to problems, just as like strings. So instead of thinking of our input as like a function and then I mean, this is what the picture is. It's not going to be a function anymore. It's just going to be a string. So I'll write function here only to cross it out. So we're going to call it sort of the input w. Now, most commonly you call strings x, but it would be too much confusion to do that because we used to call the indices x. So I'm going to call the string w for word. And I'm also going to change from the Python convention. I'm going to call the positions 1, 2, 3, 4. That's also a little bit more standard. Still use capital N for the number of entries. And OK, so now this string w is a string in, I suppose, colors to the n. Actually, people more often call this symbols or alphabet rather than colors, but I don't want to change everything on you, so I'll leave it as colors. And I'm also going to call the indices I. That's more natural. So I equals 1, 2, 3, 4 instead of x, because it's sort of weird. OK, so hopefully you can get over that. So let me talk about this very thing I'm erasing, the access to the input. So in this query complexity model, there's like an input, w, which is now a string over some symbols or colors or bits maybe. And you can query its entries. So you don't get to just see the input. It's sort of unknown to you, but you can ask for its values on different positions. And every time you ask for its value on a position, that costs you 1. OK, so just under this notation change, in the classical model, the setup is that you query I of your choice from 1 up to capital N. And then you get back w sub I. OK, and all the while, you're trying to decide something, some problem phi about w. OK, for example, in the Grover problem, the set colors is just bits. So you just have like a string of capital N bits, and you're trying to decide the OR of those bits. If there's at least 1, 1, or maybe you're trying to find a position where there's a 1, and what is the mechanism? You're allowed to query bits of the input, and you're charged 1 every time you query. So that's the classical model. Quantumly, it's that's what it always is, but since there's new notation, I'll remind you. So here you can query superpositions. Like sum I goes from 1 to capital N of alpha I. OK, and that counts you 1. OK, you pass it into what might be called Q sub W now. And really, there's this whole answer register thing as well. So you should pass in something like B in the answer register. And what you get out is a superposition of answers, I tensored with Wi, sort of XORed with B. OK, so again, you should think of the colors, Wi, as being represented by strings in some way. And the answer gets XORed into the answer register, which you usually just plug in all zeros here. And so then this becomes the answer. OK, this is what we've always seen before, just in in new notation. Any questions? OK. And finally, when we talked about, for example, Simon's problem or Grover's problem, it was typically like you were promised that there was at least one 1, and your task was to find that one. But it's like moderately more simple to focus on decision problems. So that's what we'll do. We're going to focus on decision problems for simplicity. What's a decision problem? It's just a yes-no problem. OK, this is just for simplicity. It makes things easier to talk about. So for each of the problems that we've mentioned, like Simon's problem, Grover's problem, et cetera, there's a natural yes-no version of the problem, which I will remind you of or tell you about. And we'll focus on that version because it's a bit more simple. OK, so specifically, now, just with this setup, so we're all on the same page, I'll give you some examples. In particular, phi is the decision version of Grover. OK, so here, colors, this quote-unquote color set is just bits. And the input now is some, you should think of it as unknown to you, string or word, W, of capital N bits. And you can query coordinates, or in the quantum case, superpositions of and the decision version is to just decide, does there exist some I such that Wi equals 1? OK, so I'm not asking you to find it. And I'm also allowing a possibility that the answer is no, that there are no zeros. OK, so you just have to answer this yes or no question. In other words, it's compute, in some sense, the OR of the input bits. OK? And this is a problem that I talked about last time. You can equally well solve using Grover's quantum algorithm in essentially square root of capital N queries. And let me tell you also about the decision version of Simon's problem. Now, this is one case where it's actually awkward that we switched notation. But every other case, it's not going to be awkward to have switched notation. So I'm going to allow this one awkwardness of the switched notation. So what is this decision Simon problem? So again, now colors is just some generic, potentially big set. And you have an unknown. The input is an unknown string W. For example, you don't know it, but it might look like this: red, green, yellow, red, green, something like this. Some length capital N string of colors or symbols. And as always, you can query I and get Wi. Or in the quantum case, you can query a superposition of i's. Now, in Simon's problem, unlike in Grover's problem, there's a promise on the input. It's not any old W. The way we're going to do it is say that it's either kind of S periodic with a non-zero S, or with a zero S, which will essentially mean that, in the other case, all the entries of W are distinct. So let me write that. So we're going to promise that there exists an S in 0, 1 to the little n, not necessarily non-zero, such that W has this weird periodicity. It's weird in this notation. So Wi equals Wj if and only if the base 2 representation of I XORed with S equals the base 2 representation of J. OK, let's, now that we're calling these indexes numbers, we have to go back to thinking of them as strings in order to make sense of this periodicity. So it's some weird thing. And the task is to decide yes or no, is S all zeros? Okay, so remember the normal Simons version, you're promised that S isn't all zeros, which basically means like these positions are paired up in a certain way. W has the same value on the pairs and different colors on all the different pairs. And now we're assuming that it's either like that or just all the colors are different. Okay, and you have to tell the difference. And you can equally well to solve this decision version of Simon using the algorithm, the quantum algorithm we knew. Basically, you just run the quantum algorithm we knew that assumed S was not 0 and found S. So you run that, and if indeed you're in the case where S is not all zeros, then that algorithm finds S. And then just as a last step, you can like check that the S you found really is correct just by picking two positions that differ by S and checking that they have the same value. And if that check fails and you're like, but wait, we proved that this check would have succeeded. I mean, this would have succeeded had it really been periodic with a non-zero period. So it must be that it's the 0 period case. Yep?
I'm not sure if you've already said this, but doesn't decision cover give us immediately a 2 to the n over 2 algorithm for SAT?
Yeah. So because the decision Grover problem has this familiar property that the computational overhead of running the algorithm is not much more than just the number of queries that are made. You do get basically a square root capital N time or gate algorithm for solving SAT. If you're given a circuit C, you convert it to a classical circuit, you convert it to a quantum circuit, you run decision Grover, it makes capital root N queries, but also basically uses not much more actual gates. Yeah.
So especially under the quantum model, it's not that clear that in general the decision problem will be as hard as the finding problem. So like for these problems, it's kind of like, I mean, probably if you think, they're kind of clear that it's about the same difficulty, right? Like finding the one of finding the or is kind of the same. But then, is it true in general?
Yeah, you're right. It's less clear that usually it's the case that if you can solve the sort of search problem, you can solve the decision problem. The opposite direction, that if you can solve the decision problem, you can solve the search problem, is less immediate. It's usually true, but like we're more used to it being like usually true, I guess, in the normal model, and maybe it's less clear in the query model. And probably it's not even obviously true. For example, especially in these, as I'm going to talk about these promise problems. Like actually, if I just gave you the ability to solve this problem, this decision problem, but then you're like, oh, but I actually want to find S in the case where S is non-zero, I don't think it's really obvious how you would do it. So really, the best thing, luckily, you can just take my word for it that like nothing disappointing usually happens. So the best thing you can do, and this is often what is the case, is that your algorithm will work in the search model, the problem where you're trying to find something, which is good. And like your lower bound will usually work even in the decision model, which is also good. So it's not necessarily, but that's how it typically is. So on that subject, there's one thing now to point out about this framework of query problems and query algorithms, or to define. And it's illustrated by the difference between these two problems. This is quite important. So we're allowing two different kinds of problems in some sense. This phi, this task, this decision task, may be of one of two types. One is called total. And that really means it's a total function, but it means that every possible, well, every string W is a possible input. I mean, subject to fixing what is the domain of colors. OK, so like an example here is this Grover problem. There's no restriction in the Grover problem on what the input is. It's literally any Boolean string. Okay, and so we call it a total problem. But we're also interested in what's called either partial or promise problems. I may use these two words interchangeably. And, well, let's the opposite. So here you're like promised that W is not necessarily anything. It falls into some set D, maybe the domain of the problem. And this is not necessarily everything. So this is like a special subset of inputs. Okay, and your algorithm is allowed to like rely on this promise. Okay, so that's how it is, for example, in Simon, where you promise you don't just get any old string. You get quite a special string that's either got this like special form of pairing up all the input colors, or it's all distinct. And what we're actually going to see is that somehow it's not so easy to get good quantum algorithms, like really good quantum algorithms for total problems, whereas it's possible to get kind of amazing quantum algorithms for the promise problems. Okay, so now we've set up, the definition of these query complexity problems, and talked about total and partial problems. And now we're going to study this model a little bit. And in particular, you can define 3 different complexities. I've mentioned them before. But I'm going to give you some notation. So let's say you have a decision problem, phi, which is maybe partial or total. So d of phi is going to be the least number of queries needed to solve a problem deterministically. Okay. And R of phi is going to be, well, the same thing with like a randomized algorithm. But let me emphasize what it means for a randomized algorithm to solve the problem. It's still a worst case model where it has to get the right answer for every possible input W, just with high probability. So it means for all inputs W, either all inputs in the total case or all W in the special set D in the promise case, it gets the right answer with probability, let's say at least 2/3. Okay, this number, as we've seen before on like homework 1, is not especially important. We'll just fix it to be 2/3. So it's not allowed to get anything, it's not allowed to like be extremely bad on any input, but like it has to be trying to be more quick on solving all the inputs. And finally, Q of phi is the same thing, but with a quantum algorithm. And again, quantum algorithms are, of course, inherently randomized, so they have the same issue. They should have the property that for every unknown input W, they output the right answer with probability at least 2/3. OK, so let's do some examples. So we'll start with this one. And you'll see, not only upper bounds, but that it's pretty easy to, in many cases, get lower bounds. So this is the decision version of Grover, or you might just call it computing the OR of the unknown bits. So I can actually even ask you, what is d of phi in this case exactly? Capital N, yes, that's right. No matter what deterministic algorithm you have, if it's going to be correct, it'll give the right answer on all bits. It needs n queries. I should, of course, emphasize that like for every single problem, there's an upper bound of capital N, because you can just query all the bits of the inputs, and then you're not charged for any computation or anything. So now you know the input, you can compute the answer freely and output it. But it's also easy to see that this is a lower bound. I mean, if you have any deterministic algorithm, that literally means, It's totally deterministic. So maybe it queries position 1, then position 6, then position 3. And it can make decisions like if it queries position 3 and sees a 0, then it's going to do position 5. Otherwise, it'll do position 10. So it's really equivalent to a decision tree, if you know what that is. But whatever is fixed decision tree or decision algorithm somebody comes up with, if it queries fewer than n bits, then you can just imagine the input that is all zeros. And every time the algorithm queries a bit, it gets a 0 in this case. But it can't stop and output 0 until it's seen all the bits, because it could be that that last bit is 1. So it's truly easy to argue that the lower bound is n. OK, what about the randomized complexity? If I'm not mistaken, you can get this exactly right, too. Yeah?
2/3 n.
Exactly, yeah. I think it's 2/3 n, or maybe ceiling of that if you want to be super fancy. Because basically, it's not hard to correctly argue that you can imagine that perhaps the input is the all 0 string, or perhaps the input has exactly 1, 1 somewhere. And it's not hard to argue that like a randomized algorithm, what can it really do except like start picking coordinates and try to find that 1. And if it ever finds a 1, then it can immediately stop and output that the answer is 1. But if it needs 2/3 confidence that the answer is actually 0, it can't really stop until it's seen 2/3 n's zeros. Because basically, if there's exactly 1, 1, in order to get like a 2/3 chance of finding it, you have to query like 2/3 of the input positions. OK, so this is not hard to prove either, rigorously. And then finally, this is what we saw last time, Grover's algorithm. Thanks to Love Grover. Interestingly, a quantum algorithm that can query in superposition can do it in an order of root n steps, queries. And further, as I mentioned before, and as we'll see next time, Bennett, Broussard, Bernstein, and Vazirani, somewhere around 1996, also showed the reverse, that you need something like root n queries. Actually, I should, I told a little bit of this anecdote last time, but I didn't tell the whole thing, which is that these people who proved the lower bound, they did it slightly before Grover. And they were kind of sad that they couldn't get up to capital N, which they thought was the truth. Grover actually didn't know about their work. So he got like root n, and he was like quite sad that he couldn't push it lower than root n. So luckily, they found each other rather soon. OK, so it's kind of it. That's the end of the story. And it's kind of pleasant because, it's resolved. We solved everything. Well, these people solved everything. Oh, let me just mention, by the way, it's hopefully clear, but this is a total problem, whereas Simon is a partial problem. OK, so what's the story for Simon? Well, both the deterministic complexity and the randomized complexity are proportional to square root capital N. Which here, we were glad because square root at capital N is small. But as we'll see in a second, here we'll be quite sad that root n is quite large. And actually, it's an entertaining exercise to think about the upper bound. I mentioned this when we first studied Simon's algorithm. But it's entertaining to figure out how to do this deterministically with root n queries. And we also talked at that time about the lower bound and why you can't really do it better than root n, even with randomness. Basically, it's kind of similar, like if the input is potentially all distinct colors versus it has these paired up colors. There's not much a randomized algorithm can do other than start picking random locations, trying to find two that are the same, and take something like root n. By birthday attack analysis to find such. OK, but, well, the point is that the quantum query complexity of this, as we saw, Simon's algorithm can be done in something like little n queries, where this is log of capital N. Okay, so this is cool because it shows an exponential separation between the query complexity of this problem and even the randomized complexity of the query complexity of the problem. And generally, like randomized is like the more fair thing to compare against when you're comparing quantum versus classical. Great, so that was great. By the way, generally in query complexity, generally problems are considered quote unquote easy if their query complexity is like a log or power of a log, polylog. Whereas it's considered hard, these are just kind of feelings, if the query complexity is like n to a power, like root n or 1/3 power of n or something. By the way, just a comment for like the complexity nerds. If you set up, you can also talk about non-deterministic query complexity and also co-non-deterministic query complexity. And if I'm not mistaken, the co-non-deterministic complexity of this problem is high. Or if you like just switch what is yes and what is no in Simon's problem, the non-deterministic complexity is high. Yet the quantum query complexity is low. So this is like, I kind of mentioned this before, like some kind of separation in this query model between the analog of efficient quantum computation and NP. Roughly speaking, because like if the input is in the all distinct case, there's no real short certificate of that. Like even if like you psychically knew like places to query, like it would be hard to like convince yourself that you weren't in the paired up case. Whereas if you're trying to convince yourself that you're in the paired up case, it's really easy if you could psychically know W. You could like just show two entries that are the same. OK, so now these are all problems that we've solved with quantum. Now I'm going to just tell you a few more problems that we haven't talked about quantumly, but they're just, they're either relevant or still related quantumly or related to other problems, or they're just other problems that we haven't thought about at all for quantum. Here's another one that's called the 2-to-1 problem, or sometimes called the, actually maybe more often called the collision problem, but this is a more descriptive name. It's kind of a variant of Simon's problem, and it's also a partial problem. But it's a partial problem with much, much less structure than Simon's problem. So the input is some string in colors to the n, as in Simon. And there's going to be a promise, but it's a much weaker promise. Either 1, all the colors in W are distinct. That was one of the two cases in Simon as well. Or 2, the colors come in pairs. But that's it. So there are capital N over 2 colors in use. Each one is used exactly 2 times. But there's no like weird structure where like the positions where the colors are paired up has to do with like a certain base 2 shift. It's just like it could be anywhere. So there's still a promise that like every color is used either once or twice, but there's a lot less structure. And well, let's think about this problem. So what do you think about the deterministic query complexity of this? Yep.
You mean n over 2 plus 1.
Very good. It's exactly n over 2 plus 1. Because I don't care exactly what your first n over 2 queries are. If you're in case 1, they'll be all different. But even still, if they are all different, you can't be sure you're not into case 2 until you've seen n over 2 plus 1 entries. On the other hand, actually, once you've seen n over 2 plus entries, n over 2 plus 1 entries, you can be sure. If they're all distinct, you have to be in case 1. Otherwise, you see a repeat. Any thoughts on the randomized complexity? Let's say guesses.
Lower 3.
Lower. Lower.
It's like it's birthday-esque.
Yeah, I mean, it's harder than this problem, but you can still do it in root n. Yeah. Because you basically just start picking random positions. And if they're all, after a while, if they're all distinct, you're going to guess that they're all distinct. And of course, if you ever see two that are the same, then you're going to know that it's case 2. So you just have to analyze how long should after a while be. And so you have to think about the problem. If you're really in this case where there's 2 copies of each, how many random positions will you have to look at until you have a chance of finding a collision? OK, and this is classic birthday paradox stuff. And so it turns out to be like root n. And you can also show that this is tight. So it's proportional to root n. OK, so it's quite an interesting question what the quantum query complexity is. So for Simon, it was teeny. It was like log n. But there was a lot of structure there. And turns out, I'll just tell you, that it's proportional to n to the 1/3. So it's kind of an interesting answer. So the upper bound was found shortly after Grover's algorithm. And it's not very hard. I kind of want to show it, but I only have so much time. I'm going to say it real fast. So here's the verbal proof of the n to the 1/3 upper bound. So you have your n coordinates. And what you do is you pick like a set of them at random. I draw them contiguously, but they should be non-contiguous, called L of n to the 1/3 coordinates. Okay? And you just query them. Okay? So that costs you n to the 1/3 coordinates queries. That's fine. And let's say A is the set of colors you get back as your answers. Well, of course, if you see 2 different colors in A, then you know you have to be in case 2. So that you're done in that case. Return case 2. Otherwise, assume they're all distinct. OK? Good. So now, you kind of ignore about these positions that you know the rest of. And you have the remaining coordinates, and take away L. It's basically still around capital N positions, because this is very small compared to this. But now you build a new oracle. We'll call it Q prime, which, when given I, it outputs 1 if Wi is in this set A of colors you've seen, 0 otherwise. And basically, this looks like a sophisticated query, but it actually only costs you 1 every time you want to query it. Because if you want to know what is Q prime's value on I, you basically just have to query Wi. And then you get some color, and then you already know all these answers A. You got them in the bank, so you can just look them up. OK, so you can kind of build this new oracle. And now you do Grover's search on Q prime. So you try to see if there's, and I should say the coordinates in n take away L. So basically, you're trying to see if there exists any other position that has a color that's in A. OK, so getting the answer to this, getting the OR, gives you the correct answer. Because if they're all distinct, all these queries will be no. And if they're not all distinct, actually, there'll be a lot of yeses. In fact, how many 1s will Q prime have in this case? In case 2, Q prime has k 1s, where k is n to the 1/3, because all of these colors are distinct. But they all have a mate in case 2, somewhere in here. So there's actually n to the 1/3 positions out here where it would return 1. And then you have to remember this thing I told you last time, that the quantum algorithm for Grover is actually better than root n if there's lots of potential things to find. So we didn't see this, although it's not hard. I think I might have sketched it, that Grover, if there are k 1s, can work with root n. Well, that's really n minus n to the 1/3, but that's negligible, over k, which is, in this case, root n over n to the 1/3 is root of n to the 2/3 is n to the 1/3. So this Grovering down here, again, costs you n to the 1/3. So it's sort of collectively on the order of n to the 1/3. OK, so that was a little bit fast, but I hope you got the gist of it. And it's a good illustration of how you can use kind of Grover as like a subroutine or a clever subroutine to solve other searchy type problems better than you might expect. But sorry to say, there's also a lower bound that's n to the 1/3. And that's actually harder to prove. It's quite tricky, actually. It was proven by Aronson. Well, he got a worse result, and then she got the optimal result around 2002. So it's quite different. It's, superficially, it looks a little similar to Simon, but the lower bound is much worse. It's not on the order of log. OK, let me tell you one. Well, I think I have two other problems, but let me tell you another problem that is quite similar to this 2-to-1 problem. It's almost like the total version of it. It's called element distinctness. And it's a total problem. And it's really just like case 1 versus not case 1. So it's just yes, no. Are all the wi's distinct? OK. And I won't get into details this one, although you can think about it. First, the deterministic complexity. It's really not hard to show that it's exactly n. Because they could all be distinct, except there's one pair now. And actually, because of that, even tougher possibility, it's not hard to show that the randomized complexity is basically n as well, up to a constant. Because it's going to take a long if there's exactly one pair that's the same and the rest are distinct, it's going to take you a long time to notice that. As for the quantum, it's not hard to show with Grovery ideas that it's at most n to the 3/4. In fact, it is hard to show, but it can be shown by Andres and Binus that it's at most n to the 2/3. That was from 2007. And there's also a lower bound of n to the 2/3, which actually follows almost immediately from this lower bound. OK, so the correct answer for this element distinctness problem is order n to the 2/3. And just as an aside, you might wonder, is this useful for anything? This has something a little bit to do with quantum cryptography. And if you could solve this problem super fast, it would maybe help you solve graph isomorphism, but you can't. Yeah, we've kind of gone away from problems that are somehow fundamentally useful. But they're natural in the context of query complexity. OK. Let me do one more example. This is a totally different example, but it illustrates one thing. We haven't even seen a problem yet where the deterministic and the randomized complexity were fundamentally different. So I'll show you one. This one's called recursive majority of 3.
We're taking a difference. One of them was n, one of them was root n.
Oh, is that right? Ah, yes. Good. This is a difference. But I'm going to show you a total problem where they're different. So this is a partial problem. Good. So this one's going to be total. So in fact, yeah, actually, let me bring this one up. I'll give you another one while we're here. This is like a severe promise problem where this colors is going to just be 0, 1. So you're given a string. And the promise is that either W is all zeros or it's half zeros. And you have to tell the difference. OK, so what is the deterministic complexity of this? Yeah, n over 2 plus 1, because If you query n over 2, maybe you see all zeros, and then you still don't know what case you're in. But what is the random complexity of this?
Some Chernoff thing?
It's easier than that. I think it's 2. Depends a little bit on what the error bound is. It's either 2 or 1. You pick a couple spots. Of course, if you ever see a 1, then you can happily output that you're in this case. And when there are, at least half of them are 1s. Let's say you do 2 queries. The probability that they'll both be 0 and like you'll be tricked into thinking maybe that it's all zeros is 25%. Yeah, at most 25%. So this is like an extraordinarily large difference. Granted, it was for like a problem with like a very severe promise. So yeah, this is why I want to bring this one up, because it's a total example. I'll just try to define this in pictures. Like, perhaps your input is this. It's important that the number of bits in your input is a power of 3 for this problem. So here's how to find out the answer that the query algorithm is trying to find. You take like the majority of all, you divide the bits into triples and take majority. And then you like recursively do that. So here the majority is 1. Here the majority is 0. Here the majority is 1. And now here the majority of 1, 0, and 1 is 1. So this is the answer. But the problem is, like, this is an unknown string with this height is h, has 3 to the h bits in it. And you're trying to figure out like what this tree of majorities would output by querying input bits. And I'll just quickly say some facts. The deterministic query complexity is n, which is 3 to the h. You really can't do anything else deterministically but query everything. I'll skip to the quantum query complexity. This is not easy, but in 2008, Reichardt and Spelek showed that it's around 2 to the h, which is like n to the 0.63 or so. This is log base 3 of 2. And finally, the randomized query complexity of this problem is extremely interesting, and it's an open problem. And like, people have really sweated and slaved to try to solve this problem. And it's known that well, first of all, it's at most 8/3 to the h. And this is easy. I leave this as an entertaining exercise. And the way to show it is, just think about the case when it's 3. And you have 3 bits, and you're trying to compute their majority. The randomized algorithm is pick 2 input bits and query them. And if they're the same, you're done. You don't have to query the 3rd bit, because that's the answer. If they're not the same, then you'll have to query the 3rd one. But even in a case where it splits 2-1, the expected number of queries you make is 8/3. OK, and then you use recursion. But that's not the best. The best thing currently known is 2.65 to the h. And there's also a lower bound of 2.59 to the h. Both of these are quite hard. This is from 2016. This is from 2015. And this is n to the 0.866. This is n to the 0.887. That's all that's known. I don't know. This is like laws like 30 square root 5 over 2 or something like that. These are complicated papers. But I only bring it up, really, just aside from entertainment value, as an illustration of a total problem where the randomized complexity is at least somewhat better. It's like n to the 0.887 at most than the deterministic complexity. OK. So we've seen a bunch of examples. And now I want to make a remark. We only ever saw an exponential gap between Q and R. In fact, even between Q and D for promise problems. In fact, we really only talked about the case of Simon's problem where there's an exponential gap between Q, the quantum query complexity, and the classical query complexity. But OK, Shor's problem has a similar phenomenon. And it turns out that this is not a coincidence. In fact, there's a theorem that says you'll never get an exponential gap for a total problem. So this is theorem proven in '98 by Eels and 4 others. Although, as I'll say in a second, basically followed from known stuff together with the quantum lower bound of root n for the OR problem. But anyway, let me just say the theorem. It says for all total problems, and let's say where the inputs are binary, although generally that's not a big deal because you can think of the colors as being written down by bits, and it's not really going to change the conclusion much. Right, this is a problem that maps a string to yes, no. That's how you can think of a total problem. It's something that maps every string to the correct answer, yes, no. The quantum query complexity is, quote unquote, not much more than the deterministic query complexity, well, to the power of 6.
Right, you wrote less.
Yeah.
Quantum is definitely less.
Oh, yeah, sorry. This is, thank you. Let me get this right. Is that better? That's better. Good. Right, so you can think of it if you have like some quantum query algorithm that makes some small number of queries R, then there's actually a deterministic query algorithm that makes at most R to the 6th times a constant queries. Or it's saying that quantum, for total problems, will never achieve a speed up that's better than like a 1/6 power. OK, so we saw for Grover's algorithm, quantum does achieve a speed up that's like a square root. And this is saying for any total problem, you will not do better than a 6th root.
Is it known to be sharp?
No, although in 2015, people were extremely excited when Ben David showed a problem that had a bigger separation than Grover, a super Grover separation. So Grover is a problem where quantum has a speed up over randomized query complexity by a 1/2 power. And he showed a problem where it was a 1/2.5 power. And it's conjecture that you can at least get a 1/3 power. But between that and 6, people don't really know. But a little bit more important, even than these factors of 6, although these, trying to get these factors right is actually also very interesting. Sort of the philosophical importance of this theorem. Well, as I said, for sort of unstructured problems, which is how I might think of total problems, where there's like no special structure assumed about the input, quantum cannot give an exponential speed up. And in fact, it can only give a polynomial speed up. That's over classical, even over randomized classical, even over a deterministic classical, granted in the query complexity model. OK, so it's some kind of interesting negative result about the power of quantum computing. Good question. You might hope to have like a tighter connection, but if you want something of the form, R is less than Q to a constant, still the best known constant is 6. So I mean, we don't care about deterministic too much. This is more fair. But the best relationship we can get here in terms of bounding randomized complexity versus quantum is 6th power. And we can also get it for deterministic, so it's like only stronger to write this fact. It's a good point, though.
So then we can't get any relationship between D and R?
I'll talk about that in a second. So this theorem is a consequence of two things. You get it by combining two things. One, and I'll get into more detail in a second, but known query complexity stuff from like 1989, having nothing to do with quantum. So they were studying this query complexity, 30 years ago, and they knew a bunch of stuff even back then, nothing to do with quantum. And so like one moderately sophisticated fact from the olden days, plus the lower bound for Grover, which, as I said, they proved around 96 or so. And again, we'll see this in the next class. So it turns out that like once you have this fact and you combine it with like known technology from the olden days, you get this result. Yep.
Is this sort of a reduction style thing where like if you could solve something faster than that, you could get a better algorithm for OR?
Yeah, you can think about it that way. You can think about that way. You'll see a bit of the structure. I'm going to talk about it. So now let me get to the question of R versus D. Because you remember in lecture 2, I spent half the lecture talking about how in the 70s and the 80s, people were randomness in computation, it's such an amazing idea, it's a new thing, it's going to fundamentally change the way we think about computation. And it's very interesting, and they studied it, and they're really into the power of randomness versus determinism. And quantum is kind of like the randomness of the 90s and 2000s, rather than of the 70s and 80s. And indeed, back in the 70s and 80s, when they were randomness, they were thinking all these same query complexity questions, just about what is the power of randomness. And so indeed, this R of phi versus D of phi problem was studied in the 80s and 90s. And it was the same phenomenon, right? People knew there was this trivial problem oh, is it all zeros or is it half zeros, where there's an exponential gap between randomness, random query complexity, and deterministic query complexity. Even bigger than exponential, actually, arbitrarily large gap. But they didn't know about the situation for unstructured problems, total problems. The best thing they knew was something like this. They knew actually there's a slightly more complicated to explain example where this number is a little bit smaller. But that's all they knew. And a hero came along in 1989, Noam Nissan. And he proved this, but for randomized. So he showed this theorem. The deterministic complexity is at most the randomized complexity cubed. And so you could say exact same philosophic import, for unstructured problems, randomized can never give you more than a polynomial speed up over deterministic, at least in the query model. So it's kind of interesting. You have the exact same, philosophical conclusion. And now I actually want to tell you a little bit about the structure of Nissan's proof. And then you'll understand these bullet points a bit better. So first of all, it's completely elementary. It's from 89. How complicated could it have been? But very clever. I mean, it's definitely clever. So here's how I like to think about his proof. So step 0 was he invented a new. Oh, sorry. This is for total. I should have said that. OK, he invented a new complexity measure of Boolean functions, which in this lecture, I'm going to call the embedded OR complexity. Which I will abbreviate to EOC of phi. The real name of this is block sensitivity. And it's abbreviated BS, but I'm going to use this because I think it's more evocative of what it's really about. OK, so he invented this, and I will explain what it is. But very briefly, it's basically you look at the function f, and at a high level, you sort of look at the largest or subfunction of it. Now, what exactly subfunction means, I'll explain. But like, you look at the largest or that's kind of embedded in phi, in a sense. But just think of it at that level for now. And then his main contribution, this is like a clever part, is to show that the deterministic query complexity of any function phi is basically bounded by some power of this embedded OR complexity. He showed power fourth power. And I cannot say too many words about how he did this. It's like a page long. It's elementary. It's clever. It would make like an excellent 5-part like homework exercise. Maybe it will. Who can say? Yeah, basically, he shows that if like the function phi is not too complicated in the sense that it like does not have a very large OR function embedded into it, then a certain naive querying algorithm for phi works effectively. It's a clever argument.
I mean, when you just have one OR function, then EOC of OR is 1?
Is n. Yeah.
Okay.
So yeah, so I should add, this is again a number that's between 0 or 1 and n. I guess it's between 0 and n, much like query complexity. And for the OR function, it's n. And it's somehow like as I said, sort of the most number of bits in a subfunction that is like OR. And basically, it's actually extremely hard to find like an example of a function where this quantity is small. But in fact, it's very hard to find functions that depend on all their bits where the deterministic query complexity is very small. OK, so I cannot say too much more about that. I will say a little bit more about this EOC in a second. But just to cap off the sketch of Nissan's result, the last thing is he just observes a fact which is quite simple. Well, we've seen it before, that the randomized query complexity of the OR function on m bits is basically m. I mean, we saw that, right? If the string is either all zeros or it has exactly 1, 1, it's going to take you about number of bits queries, even randomly, to tell that difference. And this, I mean, once you understand that this embedded OR complexity, I assure you this sort of trivially implies that the randomized complexity of any phi is at least the embedded OR complexity of phi. Because at a high level, this is like the size of the largest OR that's embedded in phi. And so in order to solve phi, you have to at least solve this embedded OR on this many bits in phi. And to solve an OR takes about as many queries as the number of bits in the OR. Does that kind of make sense? OK, and then if you just chain together this, this and this, yeah, you get that d of phi. Just combining 1 and 2 is at most r of phi to the 4th. Well, I said you got 3. OK, you can add like some trick somehow, and you can get it down to a 3. But like, let's just leave it at 4. The philosophical import is the same, whether it's 4 or 3. OK, but once you know this, the only thing that this really used about the randomized model of query complexity is that OR, computing OR, was costly. And now, I mean, once we knew this fact in 96, we can use the exact same proof structure. So like a new 2 prime, once you know that the query complexity of OR on the quantum query complexity on m bits is still pretty costly. It's at least root capital M. Then again, I assure you this trivially implies that if a function kind of has an OR on m bits or on EOC of phi bits hidden inside it, then the quantum query complexity has to be at least the root of that many bits. Okay, and again, if you change chain 2 prime together with Nison's very clever number 1, it implies that the deterministic query complexity is at most the quantum query complexity to the 8. I told you it was 6. Okay, Beals, et cetera, got like a little trick and got it down to 6. But again, whatever, 6, 8. Okay, does that kind of make sense?
Yeah, question. So
Yeah.
if there is any results that's known about the randomized complexity being at most USC or something?
Yeah. Yeah, so these are all known to be related. So what's known is, I forget the exact relationship, but there's something like, it's a good question. In fact, both of these things are, in fact, the deterministic, okay, yeah, all of these things, they're all at most EOC to some power. I forget what it is. Maybe it's 2 or something. But yeah, in fact, this shows that like the deterministic query for total functions, the deterministic query complexity, the randomized query complexity, the quantum query complexity, the embedded OR complexity are all polynomially related. They can be, different powers of each other, but they're all, either quite high at power of n or quite low, like a polylog n. Okay, so I mostly want to end there, but I guess I'll say just. Okay, I was going to try to explain the embedded OR complexity in like a natural way, but I think maybe since I have very little time, you can read the notes. Let me just actually write the formal definition, which is on one hand more complicated to explain than the intuition, I think, but on the other hand, it's shorter to write. So here's actually the formal definition of the embedded OR complexity of phi, also called the block sensitivity. It's the maximal number m such that there exists some input string w. In the case of the OR function, w will be the all zeros string. And 2, m disjoint sets of coordinates. We'll call them j1 through jm. In the case of the OR function, these will be like all the coordinates taken as singletons. But in general, they can be blocks, hence the name block sensitivity, such that phi of w is different from phi of w where you negate all the entries on block ji for all I. So basically, say in words, this embedded OR complexity is high. It's at least m if you can find some string w of zeros and ones, plus some like blocks of coordinates. Here's like I found 3 blocks of coordinates, such that on one hand, if you apply f to this string, you get some value, perhaps 0. But on the other hand, if you take any single block and flip all the coordinates in that block, f's value flips. And you see that's a function of the property of like the OR function, right? Like there, the string w is all zeros, and the blocks are just single blocks. Okay, and this has, it's sensitive to flipping any block. So if the OR function applied to all zero string is 0, but if you flip any one block, it flips the value to a 1. So it's kind of like a point for where the function is like very sensitive to like flipping bits or blocks. Okay, and like in general, like you could have some maybe some function like this, w1 and w2, or w3 and w4, or w5 and w6, or et cetera, which is like kind of like an OR of like ands of 2 bits. Okay, so again, if you take the all zeros string, the function's value is 0. But if you flip like both coordinates in any block, that flips the value to 1. Okay, and this guy's embedded OR complexity is like n over 2. So it's some kind of like OR-like thing. And like the AND function has embedded OR complexity n, because like on this input, all 1s, the value of the function is 1, but like you can take every bit to be a block, and if you flip it, the value is 0. So it's really not too hard to show that it's basically not too hard to show that if you could compute like a query algorithm could solve a function whose embedded OR complexity is m, it's like only easier than solving the OR function on m bits. You have to think a little bit about why that's true, but that's the idea. OK, so I'll stop here and see you next time.